actually pretty easy. And this technique has its limitations. It tends to focus on planetary systems that have short periods, but nonetheless, it's very useful. And one of the things I find amazing is that you can go outside with a celestron with a CCD on it, and a number of amateurs have started tracking these objects, and you can get one of those light curves. And this one was done by an amateur astronomer in Finland, and he got a very nice light curve as the planet HD 209458b goes around its parent star. But the reason we're interested in them for JWST is because you can do so much more using this technique. And the great thing I think about it is you don't actually have to image the planet to be able to do it. So we can figure out all these really neat things without ever actually having taken a picture of the planet. So this is just an example of how sensitive this technique is. So another one of these systems that we know of now where a planet goes across the face of a star and we can measure the signal is TRESS-1. And TRESS is the name of the survey. It's run by one of my colleagues, Dave Charbonneau. And when they were looking at the transit for this particular object, they were surprised to see this bump. So you see the light coming from the star is constant, and then the planet starts to go across just here. The light starts to drop, and it's not dropping very much. It drops, and then you have a bump, and then it comes back up. And what we're actually seeing here is this bump is due to the fact that the planet is going across a sunspot on that star. So you can actually use this technique to see sunspots on other stars, again, without ever actually taking pictures of them. And then we get into even more interesting possibilities. If you take pictures of these transits of different colors, you start to see some interesting things. You see this region here where the lines don't overlap. Well, that's because you're seeing a contribution coming from the atmosphere of the planet. And this movie will hopefully explain why that is. And if we just wait for a minute, here comes the planet. And you see that orange ring around the planet. That's the planet atmosphere. So for a small annulus of the atmosphere around the planet, we have starlight coming through that ring of atmosphere, and you can separate out that starlight and get a spectrum of the planet. So you can get a spectrum of the planet's upper atmosphere by doing this. So again, without having to take a picture of a star, you can measure a spectrum. And we've been able to do this so far with two objects. The Hubble Space Telescope, coming back to our friend in Finland here, the Hubble Space Telescope was able to measure potassium in the atmosphere of this planet, 209458a, I guess they called it. And more recently, Hubble's been able to get a spectrum that shows evidence of water and methane bands in this exoplanet going around a star with another phone number, HD 109733b. And this is actually the spectrum of an extrasolar planet. So that's pretty amazing. And the problem with this technique is that you need to have lots and lots of light to do it. It's kind of strange to think that you can see these things with a celestron telescope, but to get the spectroscopy, you need to collect an extremely large amount of light. So having JWST do this means we'll be able to study a lot of these objects and be able to start looking at how exoplanet atmospheres differ from one another. It's a new field that's being called comparative exoplanetology. And it's brand new and just starting, as you can see, with this object and the one I showed you before. One of the other interesting things about these transits is that it depends only on the ratio of the radius of the planet to the radius of the star. And so if you look at older stars which have smaller radii, that ratio gets to be more favorable for looking for other kinds of planets. So this is an M star, and compared to it is Neptune. And then if you look at an even later star that has a smaller radius and compare it to several Earth radii, so-called super-Earth, you find that they all have transit depths of about 1%. And what that means is that we will be able to try to do these observations with JWST, possibly of the atmosphere of a super-Earth. And that's a really big deal. And this figure, again, just illustrates the relative size of different stars against a couple of well-known planets. So size really has a big effect. So if you look at later type stars to look for systems that have transits, you'll be able to find interesting planets that are more like the Neptunes and Earths in our own solar system. Now, there are some interesting aspects of this. One of them is that these systems have relatively short periods, especially the ones that go around the later type stars. And astronomers have this thing they call the habitable zone, which is where water can be liquid in our solar system. And we're down here. This is the Sun, this is Mars, Venus, and this is Earth. And you can see we're slam dunk in the middle of the habitable zone. But as you go to stars that aren't as hot as the Sun, that habitable zone moves in. So it turns out that the objects you would be looking for to find super-Earths around these smaller stars also are the ones that would have a habitable zone in a region that you can study. So there's a lot of potential there, and people are really excited about what you could do with JWST. Now, time is starting to press, so now I'm going to move on, having told you about the science, to the last part of the talk, and that is what are we doing to build this telescope, and why is it so hard, and what are the challenges, and how are we addressing those challenges? So, I talked already about the key things that this telescope needs to do. The first one is the sensitivity, which is the big mirror. And so we said that we need at least a 6.5 meter mirror, and we need it to be diffraction limited, or the sharpest possible at 2 microns. We also need it to have a low background, so it's got to be operating at 40 Kelvin or 40 degrees above zero. And we want to launch it on an Ariane 5, which is one of the largest fairings at the moment on rockets. But we're still going to have to unpack it once we get up there. So it's try again. Whoops. So this, sorry, went one too far there. This is what JWST looks like, and let me now explain to you why this telescope looks so different. So this is the mirror, the primary mirror, and it's not just a single mirror. It's 18 individual hexagonal segments put together to form one mirror. And each of those segments can be moved independently. Then we have the secondary mirror here, and a whole secondary mirror structure here can be folded away. So this whole region of the telescope is going to be cold, but we still need to see the sun to get power for our solar arrays, and we have a lot of electronics boxes that really don't like running at 40 Kelvin, so we have to keep them hot and keep them on what we call the sun side. So the solution we came up with for having a telescope that has to be cold and a spacecraft bus that has to be hot is to have what we call a sun shield. And my wife had a real hard time. She's the one who did these, the Italian notes on this. She had a real hard time coming up with a word for this, so I hope the translators are having fun. We call it a sun shield. You can think of it as a big beach umbrella. If you get hot on the beach, you can just sit under the umbrella and it blocks out the sun. And that's basically what this does. It blocks this side of the telescope from seeing the sun. It's about the size of a tennis court, and it's 5 layers of mylar membrane. And it all has to be unpacked and unfolded once we're launched. And I'll come back in a minute and show you just how we're planning to do that. And if you think of it in terms of suntan lotion, has an SPF of about 1 million. So it's got to do a really tough job here. The instruments for the telescope all sit in this box back here, and they're an integral part of the cold part of the telescope because we need to keep them cold. And then on this side we have the spacecraft bus, and you have all the usual things. You have a solar panel, and this one's called a tail dragger. And then we also have something called a momentum trim tab. And one of the problems with this telescope is that sun shield is so big that it actually we start to build up significant momentum from solar radiation. And this helps us balance that and get the maximum performance. Otherwise, the telescope will start to tip over, left to its own devices. And I think I pretty much covered everything there. And then we have this thing here is called a UPS. This is what we keep the sun shield in. You can see it better just there when it's on the ground before we deploy it. Now, there's a lot of challenging technologies in there, and everything in space is hard, but everything in space that's cryogenic or has to run at 40 degrees Kelvin is 10 times as hard. So everything you do with this telescope, you have to think about how to do it. Then you have to think about, will it work at the temperature it's going to have to operate at. And we have to think about how to align the telescope on the ground and have it still work when it's cooled down to the temperature we're going to operate at. So there's a lot of challenges. So these just summarize some of the key technologies, and one of them is the backplane. And you can't really see much here, but this hexagonal structure here is the composite carbon fiber backplane, and that's what's behind these mirror segments. So that has to be built to such a tolerance that when it cools down, the figure of the primary mirror moves by nanometers. It's a very tough engineering problem. Then we have a range of sensors that have to work in the infrared. And because electronics are this side and our detectors are that side, we have these special chips that digitize the signal and send them to the other side of the telescope. And I guess a way of thinking about this is if you have a digital camera and then you have to run your signal out to the rest of the camera, which is in a different room. You need something to keep the signal at a level that you can keep it clean all the way down that cable. And this is about 6 meters of cable from here to here. So you have to have special digital circuitry to handle that. Microshutters are something that I'll come back to, but it's a technology that's been developed for the European spectrograph. We're building these at Goddard. And it's basically approximately 400 by 500 array of little shutters. They're about 200 by 100 microns. And you can open the ones that you want to be open and close the rest. And it allows you to very selectively pick what you're going to observe. So this is what's called MEMS technology. Then we have a solid-state cryocooler that keeps one of the instruments operating at 7 Kelvin because the mid-infrared needs to be even colder. And this was chosen primarily because we couldn't tolerate the mass needed for a cryogen tank like the Spitzer telescope. The membranes for the sun shields are a major technology. They've got to be there for 10 years. They're going to have micrometeoroids hitting them. They're going to be seeing the sun every day, full intense UV radiation. So we want to know that in 10 years they haven't turned to powder or ripped or torn during deployment. So there's a lot of thinking that had to go into doing this. And then once you get past the basic technologies of will they last for 10 years, you've got to think about, well, how do I pack up a candy wrapper the size of a tennis court and get it to come out again when I ask it to without getting all wrapped around itself or caught up on stuff. So this is very challenging technology. The mirrors here are hexagonal segments, and this is a picture of one. We've done a very systematic development of this technology. It's called beryllium. We're using beryllium mirrors because they're very light, they're very stable, and they work very well at this temperature. The downside of that is that they take a long time to make. And then finally, we don't have a single mirror here. We have 18 individual mirrors, so we've got to have a way of making them all come to the right place so they act like a single mirror. Now this figure just shows you the basic structure of the telescope. So this is the primary mirror. The light comes into the secondary, and it goes through this baffle here, comes out the other side, and there's actually a third mirror in this system. It's called a 3-mirror anastigmat, and this mirror is called the tertiary mirror, and that then sends light to another mirror which controls the pointing. Now, as I said, the mirrors on this telescope have been a real challenge, but we've managed to address them all. So they start their life as a big block of raw beryllium. This is what it looks like. And we cut that in half, and we get 2 mirror segments like this. And what we then do is we machine away 95% of the material to lightweight them. So the mirrors look like this is the back side of the mirror, and you can see this hexagonal structure. It's basically where we've taken out most of the material to make them, keep them stiff, but make them light. And each mirror actually weighs about 25 kilograms. It's 1.5 meters across. You can pick these things up. It's not recommended, but you can. And then this is the secondary mirror, and that's bigger than the primary mirror on Spitzer. And then this is the tertiary mirror, that third one in the chain. Now, once we finish cleaning them up, they get sent from the guys that did this in Axis in Coleman, Alabama, and they go to Tinsley in Richmond, California. And Tinsley have a long tradition of doing astronomical optics. They did all the mirrors for Hubble instruments that corrected the spherical aberration. So they're real experts at doing this. and they polish this very hard metal. And